Welcome back. So, on the last video, we we were calculating, um, we were solving the example 2.15, which is how to calculate transformation equations and how to interpret a given text, how to interpret a given task that a robot it has to perform. So we start the last video warming up with the example of 2 or 3 past videos, and then we start um, to solve the example 2.15. So we base it on the informations of the text and on the task that this robot it has to perform. We were able to extract a transformation equation, and we apply inverse transformations in order to simplify this transformation equation. And then we apply properties of inverse transformations, inverse matrices. So we were able to get in a more simplified equation which describes the motion of this robot, the motion that this robot it has to do in order to achieve a certain task, and which on this case is it was to um, using a camera attached on the fifth link of this robot, and this camera is recording or is pointed on the direction of some object. And we simplify this equation, and the problem give to us the information of the transformations in form of matrices. So on the first example that we used to warm up, this example we're not working with matrices, but on this example we use matrices, and what we have learned is when certain link and angles of the joint, when they are defined in a matrix form, and now you know that the matrix represent the transformation and vice versa. The transformation represent the matrix which contains the informations of rotation, the informations of if we are talking in relation to this column, it contains the information of the position or rotation of certain rigid body, where is localized when we are referencing to the fxyz reference system. And using these defined transformations, we calculate the transformation that this robot it has to do in order to achieve this task, which is the transformation of the frame of the robot in relation to the frame of the end effector. So I explained that the end effector is the frame, is the part of the robot responsible for perform a certain task, like record a certain object or do a task of drill a hole in a workpiece, or when we are working with a robot that we wanted to this robot grab something. So the end effector is the part of the robot responsible for do certain task. And even without knowing nothing about any information, any description, if any description are passed to us, and even if we do not know nothing about the task that this robot has to perform, we can write a transformation, which is obviously is the transformation that uh, tell to us where this robot is going, where the end effector of this robot is going to be at the end of the task. And now, I said that on this video, we will start um, the introduction of forward and inverse kinematics. So I already write what is on the book, and so let's start. Okay, is the topic 2.8, and to introduce this topic, I will just read what is telling to us. Okay, so let's suppose that we have a robot in which its configuration is null. And that means the length of the links and joint angles are known. The calculus of the position and orientation of the robot hand is called forward kinematics analysis. Okay? So if all joint variables of the robot are known, using forward kinematics equations, we can calculate where this robot is going to be at any moment of its motion. If you want to put the hand of the robot in certain desired position and orientation, we need to know what are the lengths of the links or the angles of the articulations of the robot, and that is called inverse kinematics analysis. And we use a procedure on the resolution of this type of problems. First, we develop the forward kinematic equations of the robot, and then we use these equations to calculate the inverse kinematic equations. And we have to remember from chapter 1 that in order to positioning and orientate a rigid body in space, we link a reference frame on it, and then we described the position of the origin of the reference frame and the rotation of its three axes, which is x, y, z. So also you have to be able to differentiate those two things, reference frame and reference system. which we already study on this series. And you know that they are the fxyz and fnoa. And a reference system, let's suppose it can be the range of the robot, the base of the robot, which you use the link, the fixed link of the robot itself, the end effector, and we already entry on the topic 2.9, which is forward and inverse kinematic equations. Forward and inverse kinematic equations. Of position. As mentioned before, the position of the origin of a reference frame linked on a rigid body, it has 3 degrees of freedom, and then can be completely defined by 3 items of information. As a result, the position of the origin of the reference frame can be defined in any coordinate. In X, as example, we can positioning a point in a space based on Cartesian coordinates, which means that is going to be 3 linear movements in relation to the axis X, Y, and Z. We can also use spherical coordinates, and that means we're going to have a 1 linear movement and 2 rotative movements. So let me write this. We use Cartesian coordinates, cylindric coordinates, spherical coordinates, and articular coordinates. So we will start with Cartesian coordinates. And let me draw the figure of the book. So we have a coordinate system, X, Y, Z. x, y, and z, and link it on this reference system is a vector, and on this vector, on the end of this vector p, so is a vector p, link it on the origin of this reference system, and at the end we have a reference frame, and right here the reference system in OA, the reference system XYZ, it turned into a reference for this other reference system. It can be confused the first moment. So is a reference system, but also a reference frame, and this reference system, it turns into a reference for this other reference system. And now we project this vector. We decompose this vector. So is px, py, and pz. These are components. We are decomposing components of this vector. And right here, we do not have a rotation. And the matrix that represents the transformation of this motion for the point P is a matrix of simple translation. And let me write this matrix. And if you remember, a characteristic matrix of a translation, it has this main diagonal filled with ones, and the rest of the terms, the entries, they are zero. So is a transformation of the point P in relation to the whole system, which you can say that this is representing is a analogy to a robot. So Cartesian and the components of the vector P decomposed. Okay, so that is a characteristic matrix of a simple translation. It has his main diagonal filled with ones. And now working on it, the notations. Uh, that is a transformation of the frame P in relation to the frame R. And this is a Cartesian transformation. And now let's recap what I read for you on the beginning of this video. There are some points that we can use, we can interpret to start solve this problem. First, let's take the procedure is to develop the forward kinematics of equation of the robot, and then using these equations of the forward kinematics that we develop, we use to calculate the inverse kinematic equation. And we calculate the kinematic inverse equation because we wanted to know, for example, where the hand of a robot in certain desired position and orientation. So depending on the place that this hand of the robot is going to be, we need to know the lengths of the links or the angles of the articulations. So we use kinematic equations because we wanted to know where the end effector, which can be the hand of the robot, is going to be a certain desired position, orientation, which resumes on the localization of this robot, of the end of this robot, a certain moment. And the forward kinematics we use to calculate where the hand, where the end effector, where this robot is going to be any moment of certain task. But if you wanted to reposition the hand, which is where this hand is going to be in terms of position and rotation, so we use inverse kinematics. So again, forward is to calculate where is it, and inverse is to change the desired position and orientation. So is one equation depends on the other, and we work with both. And maybe we can already solve a example. So the example 2.16. So let me write. So we want to know the position of the origin of the reference frame of the hand of the robot. Of a Cartesian robot. On the point in the point P if the coordinates 3, 4, and 7 and ask to us to calculate the necessary motion in Cartesian coordinates. So first, taking this procedure, the first thing to do is to develop the forward kinematic equation, which means that we need to write transformations, and this we already have learned how to do it. So is a transformation of the point in relation to the reference system of the robot, but we wanted to know how to do this movement, this task in Cartesian coordinates. So is Cartesian transformation. And we already finished this because it was passed to us the coordinates of the point P, which are these decomposed components. So we know that is a transformation of translation. And you know that this T, it means transposed. So we just need to place these coordinates right here. And again, we add this this line is a scale factor. Use it to maintain this matrix on its quadratic form. And that's it. Cartesian coordinates is very simple, and on the next video we will start to work on cylindrical coordinates, which is more complex. And for now, that's all. Thank you. See you on the next video.